Why, hello again. Today I'm going to talk a little bit about coordinate systems. This will be a flashback to Lecture 2, where we talked a little bit about the coordinate grid. If you'll remember, coordinate grid's got a y-axis here, an x-axis here, and you can specify any point on this grid by giving the x-coordinate and then the y-coordinate. This grid is actually called a Cartesian coordinate grid. You'll also notice that it's a 2D grid, which means that it's flat. It's a plane. As it turns out, our Cartesian grid isn't the only kind of coordinate system that's two-dimensional. There's also the polar grid. This is really useful when you're talking about circles. In the polar grid, instead of talking about x and y, you talk about the radius and an angle. Usually the radius is called r. Here the radii are marked off. 1, 2, 3, 4, 5, 6, 7. These correlate with the little lines. On this red line we have radii of 1, 2, 3, 4, 5, 6, 7. We can also measure the angle. This is the angle. It's usually denoted as the Greek letter theta, which looks like this. In polar, we usually write our ordered pairs like this, r, comma, theta. Thus, we can specify any point on the grid using a radius and an angle. For instance, let's say we've got a radius of 2 and an angle of 75 degrees. That point is, here's radius of 1, radius of 2, and 75 degrees. So that point would be right here. You can talk about any position on a polar grid, even where a polar bear is. So that was another 2D coordinate system. What if you want to talk about 3D? Well, there are a couple of options. First off, we have the Cartesian system in 3 dimensions. Here are familiar x and y axes. If we want to use 3 dimensions, we have to make up another axis, the z-axis, like this. Think of the x and y axis as being in a plane, like on a sheet of paper. Then you stick a pencil through the center of your sheet of paper. That would be the z-axis. If you're having trouble visualizing this, have no fear, Rubik's Cube is here. In a Rubik's Cube, you could think of this vertical line as the z-axis. You could use one of the horizontal lines across the bottom to be the x-axis, and the other would be the y-axis. Good luck solving this cube, it looks tough. Here's another type of 3D coordinate system. It's called the cylindrical system. The cylindrical system looks like a whole bunch of polar graphs stacked on top of each other vertically. You can see we have the polar system here. Here's our r value and our theta. To make it 3-dimensional, just like in the Cartesian system, we add a third axis, the z-axis. This isn't too complicated. This h here is representing the height of a point, which is its distance up on the z-axis. Cylindrical coordinates can be very useful when dealing with magnetism. Under certain conditions, a charge in a magnetic field will undergo a type of spiraling motion like this, which is much easier to talk about in cylindrical coordinates than traditional Cartesian coordinates. There's a third type of coordinate system in 3 dimensions that is also very useful. This is called spherical, and it's a lot like a bunch of spheres all put together. In spherical coordinates, you have to specify the radius of your sphere, rho. This is the radius on which your point falls. You also have to specify a theta, which is the distance from the x-axis the shadow of your rho casts. This is a little bit tricky. Then you need a third coordinate, which is the distance of rho from the z-axis. This is also an angle. This might seem confusing, but don't worry about it too much. We won't be doing anything fancy in spherical coordinates. It's just good to know about what types of coordinate systems are out there. Meanwhile, we'll be keeping it simple on our coordinate grid, our 2-dimensional Cartesian grid. See you next time!